So we will continue to discuss on the topic on advanced marine structures. In the last lecture we discussed about 4 theories of failure. We understood the importance of why we should study the theories of failure, because when you take the simple tension test as the reference or the benchmark test based on which we compute the yield point stresses, which is considered as one of the failure criteria when the stress reached yield point as far as plastic design is concerned. But simple tension test has parallelly other problems, that many of the values simultaneously reach their optimum value, like maximum shear, maximum strain energy, principal stress, etc. So we really do not know which will yield or which will lead to the actual category of failure. Will it be because of yielding or is it because of fracture, and what is the application of the theory, because in certain domains, in certain theories, we said in quadrant 1 and 3 they do not agree, and quadrant 2 and 4 there are serious discrepancies. The fifth theory which we will discuss today will be the maximum distortion theory. This is also called as von Mises theory. This theory was proposed by von Mises and Henke, as we saw yesterday. So the statement of the theory is already given in the last lecture, we will not repeat it here, we will straight away go to the equation. We already said for a triaxial stress state, the strain energy per unit volume absorbed by the body is given by equation. We can say, neglecting the higher powers, the volumetric strain can be expressed as epsilon 1 epsilon v is 1, 2 and 3, where epsilon 1 and epsilon 2 and epsilon 3 1 by E of sigma 1 minus sigma 2 plus sigma 3 this is 3 1 by E of I call this as equation number 3. I can substitute 3 into and get EV. So substituting equation 3 in equation 2, getting the volumetric strain. The volumetric strain, simply substitute and summarize. I can write it like this: 1 by E of sigma 1, sigma 2, sigma 3 minus 2 mu of, because each one of them have 2 products. You can see here sigma 2 is twice, sigma 1 is twice and sigma 3 is twice, 2 mu of sigma 1, sigma 2 and sigma 3. So we can also write this as 1 minus 2 mu by E of sigma 1 sigma 2 plus sigma 3. Call this equation number 4. This is my volumetric strain, neglecting the higher powers of the equation 1. So, if you look at equation 4, we can make a very important statement. From equation 4, we can see that volumetric strain is the sum of 3 principal stresses when the sum vanishes or when the summation is 0. Then the volumetric strain vanishes from this equation. So, what does it mean? It means that the body will be subjected only to distortion. That is what it is. Volumetric strain will vanish. Now, the total strain energy consists of 2 parts. One which is associated with volumetric change in the body, the other is associated with distortion, which is otherwise change of shape. Remember, change of shape and change of volume are not same, only the shape changes, volume may remain same. This is what we call as distortion. So, for 0 volumetric change, because I want to study the maximum distortion theory, therefore I should say that the volumetric change in the body is set to 0. For 0 volumetric change, as you see from the statement, the summation of the principal stresses should be equal to 0. Okay, let us do that. For no volumetric change in the body, the summation of principal stresses should be equated to 0. Then you will get pure distortion. Let us say sigma 1 plus sigma 2 plus sigma 3 is set to 0. Now, if sigma 1 equals sigma 2 equals sigma 3 is P, then P then there will be no distortion because the summation is not 0, is it not? Summation is not 0. So, let us say P is now equal to an average of this. If P is set as an average of this, it means we can schematically express this let us say will be equal to summation of two things. What we wanted is a triaxial stress state I can say now this will be equal to, we already said they are equal to P, we already said they are equal to P. And there is no going to be any distortion. In that case, we say that the stresses additionally created here, let us call them as sigma 1 dash, 2 dash and 3 dash respectively. So, we can write simple equation saying that sigma 1 is P plus sigma 1 dash, sigma 2 is P plus sigma 2 dash, sigma 3 is P plus sigma 3 dash. Let us call this equation number 7. For no distortion case, sigma 1 dash, sigma 2 dash, sigma 3 dash should be set to 0. If this exists, which is not equal to 0, but if sigma 1 plus sigma 2 plus sigma 3 is set to 0, no volumetric change. For sigma 1 dash, sigma 2 dash, sigma 3 dash set to 0, no distortion case, okay, two explicit cases. But the triaxial stress test is a combination of this. What I am saying is instead of 1, 2 and 3, I am saying this as P and C, okay. So, this is going to be a combination of these two cases. In that situation, let sigma 1, sigma 2 and sigma 3 be P be substituted in equation 1. Equation 1 is the total strain energy value. Just see the equation 1. I am rewriting it here. U is given by 1 by T of sigma 1 square, sigma 2 square, sigma 3 square minus 2 mu of sigma 1 . Is this the equation 1? So substituting this, I may get 3p square by 2e 1 minus 2 mu. Is that okay? Equation already we can also say from this figure that sigma 1 plus sigma 2 plus sigma 3 is 3p plus sigma 1 dash sigma 2 dash plus sigma 3 dash, is it not? I call this equation number 8. So now I can say u is 3p square by 2e of 1 minus 2 mu, equation 9. So we already know P is sigma 1 plus sigma 2 plus sigma 3 by 3. So substitute in 9, so U becomes one minus 2 mu by E of this 3 and this 3 goes away, simply sigma 1 plus sigma 2 plus sigma 3 the whole square. Okay. Equation 10. So if you really wanted to find the distortion energy, can be found by actually subtracting equation 10 from equation 1, because equation is a total strain energy which has volumetric change plus distortion both, is it not? I subtract this from 1, I get the distortion only. So let us do that. So U distortion is U minus U volumetric so let us do that. U distortion, get this equation, let us see. We have equation 1 is showing U and UV is above, this is actually volumetric. This is going to be 1 minus 2 mu by 6e, no, because this is square, it is going to be 6e. Please make a change here. When you substitute back here in equation 9, because it is square, get 6e here. 1 minus 2 mu by 6e of the squares of this. So substitute from U minus UV and get me U distortion. See what equation we are getting. So it is going to be 1 by 2 E of sigma 1 square sigma 2 square sigma 3 square minus 2 mu of minus 1 minus 2 mu by 6 E of so after simplifying 1 plus mu by 6 E of sigma 1 minus sigma 2 the whole square sigma 2 minus sigma 3 the whole square sigma 3 minus sigma 1 the whole square, equation 11. sigma 1 minus sigma 2 1 plus mu by 6e, then simplify and check. So, for a uniaxial stress state sigma 2 and sigma 3 is going to be 0, so u distortion, and we all know that sigma 1 is going to be yield value, that is the definition of the theory. So, u distortion is going to be, what will be the value? One plus mu by 6e of sigma yp square. Of twice, because there is one square here, one square here. So, I can say this as, okay. So, equation 12, because there are two squares, one is sigma 1 here also, one sigma 1 here also, remaining all are 0. So, the condition of yielding according to maximum distortion theory is given by sigma 1 minus sigma 2 the whole square to sigma yp square. Call C question number 13. So, for a plane stress problem, this equation can be, that is sigma 3 is 0 biaxial stress state. This equation can be sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2 is going to be 2 sigma yp square. The 2 goes away here because there are 2 here, sigma yp square, which is again an equation of an ellipse. The 2 goes away here. There is 2 here in all the cases, the 2 goes away. It is an equation of an ellipse. So, equation 14 represents an ellipse. So, let us draw the failure boundary as indicated by the maximum distortion theory and see what are the discrepancies in different quadrants as we saw in the earlier theories. Let me draw this theory boundaries. So, these values are all sigma yp's, and the minor axis values will be sigma yp by root 3, you can check that. And this value is more or less equal, okay. My figure may not show that, even this is also sigma yp, this is also sigma yp. So, you can very well see this theory in the first and third quadrants, it is agreeing more or less with the maximum principal stress theory, okay. Whereas in quadrants 2 and 4, the maximum principal stress theory says that the stress will be equal to sigma yp, because this is the maximum principal stress theory. So, in quadrants 2 and 4, this theory says that the maximum stress will be equal to the yield value, whereas in this case it is only 1 by root 3 of that, okay. So, there has been a good discrepancy in quadrants 2 and 4 given by the distortion theory compared to that of the maximum principal stress theory. So, it has been seen experimentally that experimental results show a good agreement of distortion theory for ductile materials. So, this theory is very good for ductile materials. There is a very important statement we want to make here. When in a biaxial stress state, when sigma 1 is very large compared to sigma 2, when one of the principal stresses is very large compared to the other, all theories lead to same results. What does it mean? All these theories hold good by concluding for an uniaxial stress state. The problem starts only when it is biaxial or triaxial, which is a fact and reality in case of marine structures, okay. When the value is very large compared to the other, then all theories will yield more or less the same results. The second observation we can make is maximum discrepancies are seen in second and fourth quadrants, that is when the stresses are unlike in nature, one is tension, one is compression. Let us quickly compare all the theories. So, I want to draw superposing all of them in one figure, okay. We have now drew the boundaries separately. I want to draw a figure where I can superpose all the theories and then discuss a comparison, okay. So, I am going to draw that figure. This sigma 1, this sigma 2. This is sigma yp, this is sigma yp, these are all positive, minus sigma yp, minus sigma yp. Let us draw with the, please open back your notes and see how do we draw the principal stress theory boundary. I am drawing it here, if I am wrong please correct me. This is my principal stress theory boundary. Okay, I can write it here as based on the Rankine's principle. The second theory which we will draw will be the maximum strain theory. So, tell me what is the speciality about the maximum strain theory given by Saint-Venance? Saint-Venance, what is that? What will be the shape of the boundary? It is going to be a rhombus. Okay. So, here the values can be even more than sigma yp, whereas here the values are lesser than sigma yp, is it not? And it will touch sigma yp here. More or less this how my boundary will look like. Okay. So, let me draw this. See, this has to pass through sigma yp. Okay. It has to pass through sigma yp. This is my maximum strain theory. Given by Saint-Venance. Let us talk about the maximum shear stress theory given by Tresca. Irregular hexagon, it came I am drawing it just adjacent to this, so that it is also visible. Okay, it is one and the same, but I am drawing it adjacent. Is it okay? So, this is my maximum shear stress theory, is given by Tresca. Let us draw the total strain energy theory. This is maximum strain energy theory. Not maximum, total strain energy, it is not maximum, there is nothing like maximum strain, total strain energy theory. So what are these values? We already have them. What are these values in major axis? Major axis sigma yp, is it? Total strain energy theory. I think it is 0.87, no? Why you people are sleeping in the class? Huh? You people are sleeping in the class, is it? 0.87 sigma yp. And what are the minor axis values? 0. Of course minus. This is the total strain energy theory. Now we will plot the maximum distortion theory. Just now we plotted it here, they all will touch sigma yp in all the corners, okay, all will touch sigma yp in all the corners. So one here, and of course all these points will be touched and so on, and this value is less. What is 1 by root 3? I get a rhombus, sorry, I get an ellipse like this. Is that okay? So this is my maximum distortion theory. And this value is 1 over root 3 of sigma yp, which I already indicated here, of course minus, and this value is 1 over root 3 of sigma yp, which is 0.57. Okay. Now you can easily write good amount of inferences from this figure or this comparison of theories in single domain. So these figures show for biaxial stress state, that is sigma 3 set to 0. It has an assumption material has the same yield point in tension and compression. Let us quickly compare Saint-Venant's theory with maximum principal stress theory. By comparing Saint-Venant's theory, which is the maximum strain theory, this one, the rhombus, with the maximum principal stress theory, which is the white one. It shows for like stresses, that is sigma 1 and sigma 2, both tensile or compressive. Magnitude may remain same, sigma 1 may be equal to sigma 2, but they are of the same nature. So, you should look at the quadrants of 1 and 3, same nature. Maximum principal stress can even exceed sigma yp without is it not? What does it say is tension causes yielding will be at higher values more than sigma y. That is what the statement is. Okay. Tension will be more than sigma yp. Of course, in case of unlike stresses, that is in quadrants 2 and 4, sigma 1 is far lesser than sigma yp. You can see here, this is my rhombus point, is far lesser than sigma yp. Two. Now I am comparing the maximum shear stress theory, that is the green one, the irregular hexagon, with the principal stress theory. By comparing the maximum shear stress theory with maximum principal stress theory for stresses of same nature, sigma 1 equals sigma 2 is equal sigma yp, which is as same as principal stress theory. For unlike nature, the variation is significant, that is in quadrants 2 and 4. See here, they are significant. Okay. The third inference, can I rub this? Are we able to follow me handwriting? The third inference is the total strain energy theory indicates failure at sigma 1 not equal to sigma yp even in first and third quadrants. Okay, that is very dangerous, it is only 87%. 0.87 it yields. Okay, 0.87 it yields. What does it mean? When your point of the stress state lies above this boundary or outside this boundary somewhere here, according to the total strain energy theory, which is shown in blue color here, failure has occurred, but according to principal stress theory, according to Saint-Venant's theory, failure has not occurred, is it not? So that is a discrepancy. One theory says failure occurred, other theory says it has not occurred. Okay, it is much below sigma yp. So what does it mean? If you say in plastic analysis you take the stress till sigma yp and then only the failure starts, if your assumption is that, this is not holding good or valid as far as this theory is concerned, because this theory says when the stresses are alike, sigma 1 sigma 2 same nature and magnitude equal, failure will occur even at 87% of sigma yp itself, is it not? So that is a dangerous interpretation. Our results of sigma yp occurring causing failure for plastic analysis and design could be over conservative, could be dangerous as far as this theory is concerned. Okay. Now let us see the second and fourth quadrant more in detail. The variations of sigma yp for unlike stresses. So I am focusing on quadrant 2 and 4 between total strain energy theory, the blue one, between the total strain energy theory and the orange one, maximum distortion theory. Is minimum, they closely agree. What does it mean? This information can be interpreted as change of shape in the body will not cause serious deviation in failure. Maximum strain energy includes volumetric as well as distortion. Maximum distortion talks only about change of shape. They agree in unlike stresses 2 and 4. Okay. So if the stresses are unlike in nature, one is compression, one is tension, same magnitude, change of shape of the body will not significantly influence the failure stress or yield stress. Is that clear? But in comparison to principal stress theory, there is a significant variation. Why? This theory says at 60% of yield failure has started, whereas principal stress theory says only at yield failure will start. What does it mean? This is for ductile material, this is for brittle material. So that is yielding, this is fracture. Okay. Though both of them talk about yield point only, remember this also sigma yp, this also sigma yp percentage, both of them are talking about sigma yp multiplier only, but this is for ductile, this is for brittle. Okay. This is what the failure theories are and this is what the discrepancies are. This we must understand very clearly before we really understand what do we do for the plastic analysis and design. So in the next class we will take up a design example and then we will talk about very important part in marine structures where we talk about shear center. Shear center is a very important aspect of calculation, it is one of the design aspect to be computed and very important because this induces torsional moment in the members, okay, in marine structures. When this kind of torsional moment will occur, what is the shear center, how to compute it for geometric sections we will see. We will also do couple of problems on using the design examples of these principle, these failure theories, couple of examples, then we will move on to shear center in the next class. Okay. Do we have any questions or any more important information or interpretation which I left by comparing these theories? The most important and eye catching information which you must not miss out is the comment or the focus of Senvenons compared to principal stress, okay, and the focus of total strain energy theory in quadrant 1 and 3 compared to principal stress. These are the two important eye catching, say, predominantly or significantly seen variations in your comparison of failure theories. So, the necessity of understanding failure theories, the necessity of appreciating the deviations of the failure theories in unlike stress regions and like stress regions is important as a prerequisite for us to really know what do we really mean by yielding for plastic analysis and design, which we said or which we discussed in the earlier lecture. So, this lecture terminates the discussions on theories of failure. This is only just a curtain raiser. If you want to really look into them in biaxial and triaxial stress state in detail, I think you should refer to some of the fracture mechanics lectures in detail for the materials, okay. So, we have just as a prerequisite, we must understand, we must know these, but still for the completion of the viewers interest, we have discussed this in detail as far as possible applicable to plastic design alone, okay. Of course, we will apply this in two examples and show how these theories actually give me numerically a different meaning, and as a designer how I am, let us say, influenced by these results. We will see them in the next class, okay.